Hi, welcome to Python Bootcamp. All right, so we're going to get started again with session 4. And in session 4, we're going to show examples of, more complicated Python scripts than what we've been working with thus far. Okay, cool. So if you guys were watching during the break, I was kind of working through a little bit of the kinks in my code. And mine is essentially pulling text documents from Project Gutenberg, which has a bunch of different ebooks just readily available online. And what I'm doing is I'm parsing through all of that information for one of the books and then coming up with a frequency chart based on the information that I pull. So I guess ahead of time, I need to let you know that you guys can't actually run these quite yet, like on your current machines, because of all of the packages and libraries that are pulling from it, and also for those either on Open On Demand or I think on your, if you're using MyFSU VLab, you also can't pull any of this information because it pulls directly from the internet and it's not connected to the internet. So this is kind of just to show you what's possible and to get you more inspired to do more Python work. So for this, there's a couple different websites associated with the code that I used for this section. And in it, it pulls a lot of natural language processing toolkit mini packages inside, and of course it's a very big toolkit, so there's specific like mini toolkits inside that I pulled directly from, including stop words and a couple others. Someone mentioned earlier talking about pandas, and this was something that I used to pull the strings and the words from Gutenberg to then make it into something that the computer can parse through and measure and calculate the frequency of all these words. In this, what I do, because obviously if you say the or and or a in a document, it's going to come up a lot more than any other word. I ended up cleaning up the data as well. And this URL here is specifically for the Project Gutenberg link for crimes and punishment. And so I pulled all of the punctuation so that it wouldn't take it as an additional word, and then also pulled all of the stop words. And the stop words are words that are essentially like the or and or a. And there's a set list even based on what language, and that's why over here it has specifically the English stop words. And this also kind of takes elements from what we've learned already in terms of for loops, if statements. This takes, if there's a, essentially it pulls all this information from the text file as, like even the punctuation itself will count as a word. So what this loop does is it replaces all of the words that have punctuation in them, or words that are just punctuation, as spaces, so they don't actually count as words. And then to measure the frequency of each word mentioned in crimes and punishment, the tokenizer basically splits up the document, which is, it's going to look more like a CSV file, and it has one as each essentially token that is measurable against other tokens. And then, so yeah, so to kind of see what we're working with, I can show, so fdis is the list of all of the frequency of the words that essentially this is like pulling from and organizing, and fdist1 is to list the 15 most common words in that list, so that way you don't get spammed with the whole list. And this has, so 784 references to this character, and then more common, the 14 other words that are most common in this document, crimes and punishment, are listed below. So to have this displayed in a graph, we use the matplotlib pyplot as PLT like we did before, to just list out the word frequencies in crime and punishment. And this is easily redone with any other text from Project Gutenberg. So I actually have here prepared a, this is Frankenstein. And Frankenstein, as it's a lot smaller of a text than crime and punishment, it processes through 3 seconds, whereas the processing for crimes and punishment is 20 seconds, but it's still relatively fast. The distribution will have changed. And those are all of the frequencies in numerical form. And then if we replace this line with this to show the top 10 most frequent words in Frankenstein, it displays it like that. So this is more, I guess, for in terms of data analysis, data visualization of just text, and you can do this for any book in Project Gutenberg with this specific code. But again, there's a lot of different steps in terms of like cleaning up the text file to make sure that there isn't just like random sets of like disclaimers and copyright terms and conditions within the document. So with that, I guess, does anyone have any questions about that, or anyone digital have any questions about that either? Okay. In that case, that's just one of the examples of using Python to do other things. So it's like, you know, this is maybe something that leans itself towards more digital humanities featured things. And yeah, so that's my example. So I'm gonna actually pass the mic off to Prasad to show his example. Also, again, apologies for like not having it so that you guys can be able to play and enjoy with it. But yeah, this is here for you to maybe copy it onto your local machine and try it there. So yeah. Yes, so it's just a matter of open on demand. It's just not connected to the internet. Yeah. So yeah, any more questions? All right, if not, I'll pass it off to Prasad.
So my example is, I have to fix a typo. I just realized it. Anyway, okay. Here you go. So the intention of this example is, I think you've all seen this COVID county level data that they show in the news and everywhere. Like, I wanted to generate something like that from the data that I pull from the internet, right? And to see if that's something I can do. So here I am getting all the data like online, like from online. It's none of the files are downloaded, so you can see. I'll explain to you as we go on, but this code is downloading all the relevant data and then calculating and generating all the plots at the end. So for that, I'm using pandas. It's a common data science tool, and Plotly to plot, it's an interactive graph, and URL lib for downloading, and something called adfibs. Um, I wouldn't go into too much detail, but um, so this I'm using Plotly because Plotly understands the county level data, like how to plot uh, countries, states, uh, up down to like county level. So it has all that built-in functionality. I don't have to, you know, find the borders of each county and give it to Python in a file. I don't have to do any of that. It's all built in the Plotly. But the caveat is it knows counties by international code called FIPS, FIPS. So it's not just for US. I mean, you can draw pretty much like, I'm sure Europe for sure, but almost like all the countries that like has the data available. Uh, so you need to find the FIPS code of each county. So for that, uh, I need the FIPS library. So Python, the one advantage of using Python is it's open source. So people develop tools like, as you go on. So you can find pretty much anything or like most of the things that you need online. So AdFips is a nice tool that'll that'll do the conversion between county name and the FIPS code. So the first step is I'm getting this Excel file with census data, 2019 census. I did it this last year, so it's 2019 census data. Notice it's an Excel file, right? But Python can handle Excel files. So I download the Excel files with Panda. So Panda is a library that can handle Excel, CSV, and JSON, and all those formats. So in this case, I download the Excel file into population pop data frame, and then I had to clean the Excel file because it has header and footer, like lines that I don't want in the beginning and at the end. So I do all that cleaning, and then give the first column a name, the county state, and then at the couple of lines later, I have to do some cleaning. Like when you download data from somewhere, the you know you spend some time cleaning the data because it's not in the exact format that you need, or you need to make some changes. In this case, some of the county names were different in the Excel file and the actual county names, like Saint ST versus Saint, things like that. So I had to fix those before I used them, and then I had to drop all the columns that I don't need. Like they have population from 2010 to 2018 to 2019. So I drop all those columns. I only leave 2019 population data for each county, and then I get uh, the COVID-19 case data from New York Times GitHub repo, because they have this GitHub repository with county level data. I think they update like in 2-3 days. So if you look at today, they have this data updated like 2-3 days prior to the date. Okay. So I download that file, and then I have to fix some things in that as well, the New York City and the New York. So clean the file, and then I get the GeoJSON counties FIPS, the FIPS county code for each county, and then I match the county codes I get versus the population data, because population data file has only county names, and I have to get the translation between county name and the FIPS code, right? And finally, I set the target date to January 17. That's when I add this example to this notebook. So you can have like, I don't think you can have today, but a couple of days before today should work as well. And then I work on just, I wouldn't go through like each line, but then I prepare my final data set for plotting the FIPS, the date, and the cases. So, and then I divide each case count with the population. So I want to see the population, the infected population, right? That's what I'm plotting in this case. So I divided the cases with the 2019 population, and then do some cleaning, and then finally I use Plotly to plot it. The for loop, I leave it alone here, but it's unnecessary because I'm plotting one day, right? But you can use this for loop to create, say, from the beginning of the pandemic to today, and then save those figures. I commented the line, the fig.write image, that will save this data of images as an SVG file, and then you can create an animation. It's pretty easy. So if you want, just try. In this example, I'm just showing the plot. Again, if you run it on Open On Demand, it will not work because the machines can't get to the internet. But if you run it on your local machines, should work. So I run it, and then I'm getting the packages installed, and takes a minute because I'm running this on a cloud platform. I have to install the packages every time I run. Okay, the packages are installed, and then okay, so that's the graph, and you can see it's interactive. You can see the counts, and you can zoom in. And you can like move it, and you can see the value of each county. I mean, you can change this to display the county name. So whatever, when you hover around, and it's all, that functionality is built into Plotly library. You just have to, find how to do it. Like, so that's the example I want to, the only reason I picked this is, one, you can handle different file types. Like you can get an Excel file online and get the data you wanted without ever opening it. Also, you can do like interactive plotting and not just XY plots. These are like, pretty complicated otherwise. But if you look at the code, it's not like really complicated. It has like probably like 30 lines maybe for what you are getting. I think it's that's the efficiency of Python, right? If you do this in like say another language, you might, depending on how available these libraries are, right? That's why I can write a small code to get this done. But if you can find the same library, same functionality, then you can do this in any language. But because Python is free, these libraries do exist, so you don't have to write these functions from the scratch. You can start where they left off. So that's my example. And if you have any questions, anything online? Okay. Then I'll pass on to Alex for his example.
Okay, so my example is on doing a relatively simple neural network to classify different images from a data set called the fashion MNIST data set, which is sort of a standardized set of black and white images that were, or grayscale images that were taken by the National Institute of Standards and Technology and NIST. They're 28 pixels by 28 pixels, and it's one of many standardized data sets that are used to test for testing of mostly neural network and artificial intelligence methodologies that are created. So neural networks are one of the more popular and rather powerful tools for doing things like image classification and looking at, and they're powerful enough that they can do a surprisingly large amount of things, and research on them has become an increasingly popular topic, and there's actually been an increasingly large amount of funding going towards research in and research using neural networks. Neural networks are also really good because if you've heard of something called a GPU, neural networks are really good for GPU processing because their structure is basically a bunch of matrices that are multiplied together sequentially, and that's something that a GPU is able to do very, very, very well. So there's a number of libraries in Python that are capable of doing neural networks. One of the most popular and powerful is something called TensorFlow. TensorFlow is developed and maintained by Google itself, and it's it's almost the gold standard of neural network libraries, and it's used by most of the industry that I've seen so far. TensorFlow has a submodule called Keras, which Keras is it's sort of a user friendliness layer on top of TensorFlow that makes it a lot easier to use. And so the point of this example is to show how you can take this fashion MNIST data set that I talked about and really quickly develop a neural network that can classify it that can actually tell you like what's a shirt, what's a set of shoes, what's a set of pants, and so on and so forth with really high accuracy. The first thing you need to do is tell the program how many different types of clothes you expect there to be. In this case, it's 10. You need to tell it what size the data set's going to be. In this case, it's 28 by 28. So 28 pixels, 28 pixels. It's a really small and low resolution picture. Each one's a really small and low resolution picture. Then you do this X train, Y train, and X test, Y test, which are just return values which are just values those are just lists of things that are given back to you from this keras.datasets.fashion MNIST load data function. What this does is it goes and looks for the fashion MNIST data set in a standard place that it knows to look, which is some Google Cloud site, downloads the data set, unpackages it, and divides it up according to what the data set says is supposed to be training and testing data. Training and testing are concepts in neural networks that are actually that you're gonna hear a lot about if you go any farther into machine learning and artificial intelligence. Basically, the training data set is supposed to be the thing that you already know all the answers for, and you want the computer to build to sort of figure, you're sort of teaching the computer how to classify images based on a set of data that you already know. So you tell the computer, okay, this set of 10 images is a shirt. This set of 10 images is our shoes. And through the machine learning algorithm, the program or the neural network slowly builds up a model that allows it to classify images correctly based on what you told it should be looking for. then the testing data set are the things that you don't know the answers for, that you want the machine, that you want the model to tell you what it is. How the internals of exactly what a neural network finds and exactly how a neural network does its classification is hugely complicated, and I think there's still a lot of arguments in academia over exactly how it works. It's one of the things that we know it does work. So now academics are arguing about exactly why and how. But the basic thing here is that what we do is then we do something called normalizing the data, which just means all grayscale images are just pixels. So 28. So it's a box of 28 by 28 rows and 28 columns of numbers that are all between 0 and 255. So what we're doing here is we're just dividing all those numbers by 255 to get them to between 0 and 1. This is called normalizing, and normalizing data is something that a lot of machine learning algorithms do as sort of a pre-processing step. So they kind of expect data to be in this very small set, in this very strict range once we do that, we convert everything to a categorical variable, which is just something internal to Keras. It expects it to be this way. And then we're able to actually build the neural network model. And what a neural network ultimately is a list of layers, so to speak. So it's a list of layers of functions that take an input and give you an output based on some internal computation. So in this case, we've got an input layer, which just takes all the data, takes all the image data and sends it to the next layer. And we've got a bunch of internal layers here that do various complicated things. And I'm not totally sure exactly what all of those things are. I've played with this until it worked. And so each one of these is a different layer that does one specific function. So the conv2D is a two-dimensional convolutional layer. So convolution is a complicated signal processing thing. But what it does is it takes the input, it transforms it to something based on this convolutional layer, and then sends the output of that to the next layer. And over time, each layer transforms the output from the last layer, and on and on and on and on and on through each of the layers until eventually it gets to the end where it says, okay, based on the output of the last layer, I want you to collapse all of these numbers into 10 individual numbers and tell me whether or not this test image I've given you, which is the input, is what class it is, whether it's a shirt, shoes, pants, so on and so forth. And that's what this last dense layer does. And Keras and TensorFlow have a whole long list of different layers you can use and you can play with, and they all do very different things and very complicated things that I'm not an expert in. But in doing this, building up a sequential model of things, a sequential model of transformations, you can get a computer to recognize images very, 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 very effectively. And so then what you do is you just print out a summary of the model, which is model.summary. You tell it how many images you want to do at once, you want to look at once, how many times to rerun the training set, and then you tell it to this model.fit is actually telling it, okay, take the training data with the answers that you already know and build the model for me. And then the model.evaluate function is just taking that model and evaluating it on the testing data. And if like the fashion MNIST data set, if you happen to know the answers for all of the images, you can then say, okay, I'm going to give you just the testing data, but not the answers. I want to see how well you do. Once you get the classes, then I'll give you the answers and you tell me how well you did. So sort of that, and so you sort of give it a test to see how well it does. And in doing this, you can actually run this whole thing and you'll end up getting, with just this little bit of code, you'll get a model that is 84% accurate. So out of a few, I'm not exactly sure how many images there are. There are, out of 128, so out of 128 images, it gets 84% of them correct. And that's not that, that was just a little bit of code, me throwing a bunch of random layers in there. You can tweak the layers. You can choose different functions that each layer is supposed to evaluate, and you can get that number up to almost 99%. The original TensorFlow tutorial I based this version on did have it like that. I just didn't want to copy and paste. So this is one very simple example of what you can do with Python. It's just all you really need is just, you need to know what a list is. You need to know how how to use functions, and you need to know how to use variables, and you need to know how to import functions and use them. If you can do that, you can build a neural network with TensorFlow, and you can actually get some pretty cool research done pretty quickly with that. So, are there any questions on that? Any questions online? Okay. And as I told people in the chat, and as we said before, these advanced examples don't work on Open On Demand right now, but when we send you the notebooks with the sort of thank you for attending email, it'll either be tonight or tomorrow when that gets sent out. These notebooks should work if you download them on your home machine. And we'll provide instructions for how to install the things you need. So what's next? Okay, so in that case, I think that's the end of the workshop. We actually finished